Here's a demonstration that illustrates the difference between static and kinetic friction. I have a truck here with one set of wheels that's locked up and the other set of wheels that roll freely. Now, let's imagine for a moment that you work at a major automaker and the CEO comes in one day, you're in the engineering department, and the CEO comes in and says, got a question for you. Is it safer to ride in a car with the front wheels locked or with the rear wheels locked, or does it not make any difference? Well, let's see. Let's give it a try. Here's our car. Let's start off with the front wheels locked. I'll just turn the car around here. Now you see the wheels in front, the front wheels, there we go, they're locked, they're skidding. The rear wheels are rolling freely. So let's try this. Is this safe? Looks good. No problem there. We went right straight down the hill. Try once more here. Good. Okay, now to get the rear wheels locked, I'll just turn the truck around, put it up here again, and now when we go down the hill, you see the rear wheels are skidding, front wheels are rolling freely. So let's give this a try now. Let's see if this is as safe as the other case. Oh, whew. I hope you didn't choose to ride in this one. That didn't look very safe at all. Try one more time, make sure that wasn't a fluke. Nope, it spun around again and crashed. So the answer is 1. It's safer to ride in a car with the front wheels locked. Now, why is that? Why is there a difference between the rear wheels or the front wheels being locked? Let's take a look at this for a moment. As we're coming down a hill, say with the rear wheels locked, front wheels are rolling. That means they are in static contact with the ground. The friction between the front tires and the ground is static friction. The friction between the skidding rear tires and the surface is kinetic friction. In general, static friction is a stronger force than kinetic friction. And so we have a stronger force on the front tires than we do on the rear tires. That means as the truck rolls down the hill, the tires with less friction go down the hill faster, and that makes the truck spin around. That's the difference. Whereas when we were going with the front wheels in front, the wheels with little friction were already in front, so they just stayed in front, and we went down in a nice, smooth way. So that's the difference. You wouldn't think there was that much difference between the rolling and the skidding tire, but there is different friction between the tire and the surface. Now, this happened to my uncle a few years ago. He was driving to the grocery store, and his little boy was in the front seat next to him. And all of a sudden, he says, "Hey, Dad, what's this for?" And he yanks up on the emergency brake. Well, an emergency brake actually clamps down on the drive shaft, and it locks up the rear wheels. So immediately, the rear wheels of my uncle's car were locked. They had less friction than the front wheels, and so they got ahead and actually caused his car to spin around. He ended up on the side of the road facing in the wrong direction. Now, fortunately, no one was hurt, no collision occurred or anything, but it's a very dangerous situation, as you can imagine. Actually, stunt car drivers use that technique to do a rapid turn. They'll go at high speed and suddenly yank on the emergency brake, their car spins around backwards, just like that. Now, there's another aspect to the different frictions that's a very nice safety feature. It has to do with anti-lock braking. Again, as we're going along with a wheel that's locked up, we have small friction there, the kinetic friction. A wheel that's rolling has the large friction, the static friction. To stop in the shortest distance, you actually want to keep the wheels rolling, so you're using static friction. You don't want to lock up the wheel. Locking up the wheel does not make you stop faster. In fact, it takes a greater distance because you're using less friction when the wheel is locked up. So that's the whole point of anti-lock braking. In anti-lock braking, even when you mash down on the brake pedal in an emergency situation, the car keeps the wheels from locking. It lets the wheels continue to turn, anti-lock, and therefore you're braking with static friction. You come to a stop in a shorter distance. Just one example of many where physics can really save lives and be very important in the real world. In fact, as we sometimes say around the physics lab, Friction is sometimes stranger than truth.
In this demonstration, I have 3 wood blocks. They are all identical wood blocks. They all weigh the same. If we take a look at the weight of the blue block, you can see it weighs about 18 newtons. Now with this setup, I have a spring scale between the red and yellow blocks. And the question is, what does the spring scale read? Does it read 0 newtons, 18 newtons, or 36 newtons? So the scale reads about 18 newtons. Now why does it read this and not 0 or 36 newtons? Well, the system is not accelerating, therefore the tension in the string between the yellow block and the spring scale must be equal to the weight of the block, which is 18 newtons. Another way to look at this is if you were to remove the red block and either hold the scale with your hand or attach this rope to a wall, the scale would still read 18 newtons.
Jeopardy is one of my favorite shows on TV. One night I'm watching it, and one of the categories was physics. That was fun. I was doing pretty well on that category. But what was really neat was when they showed one of the clues. It was a video clue, and Jimmy from the Clue Crew did it with a slinky. And the thing that was really neat about it was he did a demonstration I'd never seen before. And I thought it was pretty cool, so I'm going to do it for you right now. What I'm going to do is suspend a slinky, just let it hang by its own weight. I'm holding on to the top end, it's at rest. What I'm going to do in a moment is let go of the top end. And the question is, what will happen to the bottom end of the slinky? Will it drop immediately? Will it stay at rest for a few moments? Or will it move up? Well, let's give it a try, see what happens. We'll do it first in regular speed, then we'll see it again in slow motion. But I think even in regular speed, you can see what happens. Okay, so here we go. Watch the bottom of the slinky. Did you see that? The bottom end of the slinky stayed put for a few moments as the top end fell down to it. So the answer is 2. The bottom end remains at rest for a few moments. So why does the bottom stay at rest for a while? Well, as it's hanging there, you can see that the coils are stretched. These stretched coils exert an upward force, and it exactly balances the downward force of gravity. When I release the top end, these coils are still stretched, so they're still exerting an upward force. The bottom end will still stay there until the top end gets to the bottom and collapses all of these coils, then it all will fall together. I think we can see it even more clearly if we try a longer slinky. Let's do that. Now here is a good size slinky. One more aspect of the slinky experiment is to compare the fall of a slinky with the fall of a ball. Of course, this ball simply drops with the acceleration due to gravity. But what about the slinky? We already know that the bottom of the slinky stays put initially. It doesn't fall at all until the top gets down to it. But what about the top of the slinky? If I release the slinky and the ball at the same time, how will their falls compare? Well, let's see. Let's see which one falls with the greater acceleration. Clearly, the top of the slinky went down with an acceleration greater than free fall. Why is that? Well, basically the same reason that the bottom stayed put. The bottom stayed put because the stretched coils above it pulled up and countered the force of gravity that was pulling down. The top of the slinky, the stretched coil, is pulling down on the top of the slinky and makes it accelerate downward with an acceleration greater than the acceleration of gravity, which is what the ball in free fall is doing. Now, of course, for the slinky as a whole, if you look at the center of mass of the slinky, that falls with the acceleration of gravity, just like the ball does. Isn't it amazing the kind of things you can learn about when you're watching TV? Who knows what you're going to find? To hold an object at rest, the net force acting on it must be equal to zero. So for example, when we lift this mass up off of the ground, the tension force on either side due to the rope must add up, the vertical component of the tension must add up to a force equal to the gravitational pull down on the mass. Now the mass isn't very heavy actually. You can see it's not that hard to lift or anything, so we're not talking about a large mass here. But what I'd like to have you consider is the following. If we want to pull on this rope a little bit harder to get the sag out of it, make the rope perfectly horizontal, how much force do we have to exert to do that? Do we have to exert a force that's equal to the weight, that's greater than that weight, or that's less than that weight? Okay, well, let's try it out. We're going to see how much force it takes to straighten out this rope. All right, here we go. Well, not straight yet. You can see it's still sagging in the middle. We'll up the force a little bit. Well, there's still a bit of sag there. A little bit more. Okay. Thank you, Max. Still sagging. You can see it never got completely horizontal. And that's because, of course, we need an upward component in the tension to balance the weight. if the rope ever did get completely horizontal, there wouldn't be an upward component. We wouldn't be able to balance the force of gravity. So there will always be some sag in the rope. And so you can see that the force we had to exert was much greater than the weight that's suspended. That means the answer is 2. Now, this is an important consideration when building, say, a bridge or some other kind of building. The forces within that structure can be much larger than the actual weight that it's suspending. This is a very important consideration for engineers or architects when they're designing a bridge or a building. They have to take into account that the internal forces can be much greater than the actual weight that that structure is holding up. They have to take that into account if they want to keep the structure from falling down. Thanks, Max.
Here I have a circle with the segment of the circle removed, and I'll roll the ball in the circle like so. Now the question is, which can will the ball hit when it exits the circle? Will it roll around to hit the yellow can? Will it continue in a straight line to hit the white can? Or will it continue in a circular path to hit the green can? All right, let's roll the ball to find out what happens. So as you can see, it hit the white can. While the ball was in the circle was keeping the ball in a circular path. Once the ball left the circle, there was nothing to act on the ball to keep it in a circular path, and the ball wanted to continue going in a straight line.